Hi, my name is Calvin Kai, and my project is focused on identifying NBA games that are worth watching. The goal of my project is to predict whether an upcoming NBA game will be worth watching or not, based on whether the game has a low point differential and is trending in the news. I think that games with a low point differential are more exciting to watch because each possession, shot, turnover, and foul carries more weight and meaning. Low point differential games also avoid garbage minutes, where the game's outcome is so conclusive that both teams substitute their starting lineup to give their bench players more playing time. Um, and for the fact that it's trending, when teams and players for a game are frequently featured in the news, it builds the game's context. It almost like thickens the plot of the game, which is, I think, um, as interesting, if not more interesting, than the game itself. So the first step is to gather the data that we need for this. So I decided to build my own web scraper, and I collected all of my data from basketballreference.com. And I decided to look at traditional box score statistics, monthly game schedules, and player efficiency rating. Uh, Player efficiency rating, or PER, is a measure of a player's overall contribution to their team per minute. It considers positive contributions like field goals, assists, rebounds, blocks, as well as negative contributions like missed shots, turnovers, and fouls, and it wraps all of those things into one number. So for my scraper, this is the scraper I used to get the game schedule. So pretty much the steps were to first build a table for each month, append the monthly tables together to get a full season, and then combine all of those seasons into one big table and save it as a CSV file. And kind of the same deal here. The if statements inside of the team's for loop at the bottom are because teams sometimes change their names and abbreviations. So the Nets actually moved from New Jersey to Brooklyn. The Hornets became the Pelicans starting the 2013-2014 season, and then the Charlotte Bobcats became the Hornets starting the 2014-2015 season. So those are there just to adjust for those. And finally, player efficiency rating, same deal here. Um, Fewer things to do because there's only one table of player stats per season. For all of this data, I only looked out post lockout NBA season, so that's 2012-2013 season forward. And the next step was to clean and store the data. So I decided to store the data in a SQLite relational database. And you'll notice another table called teams, which is just a table with each team and its abbreviation. I also created another new database called Team PER, which attempts to capture the season efficiency of an entire team. Because PER is a per minute statistic, I multiplied each player's PER on a team's roster and their total minutes played on that team, and then summed over each team. I also did some SQL queries to combine schedule box score stats and schedule PER stats. And then I removed some missing values because my box score stats didn't include postseason games, but my schedule did. And now for data exploration and visualization. So for each variable, I pretty much graphed the distribution, a scatter plot of that variable against, first I did points scored, and then later I did point differential, and then I calculated the correlation. I also calculated outliers, but never decided to remove them because from visual analysis, none of the outliers seemed to negatively impact the correlation. So the first thing I did was define a helper function for removing the outliers. And then I just went right ahead and started looking at the distributions of field goal percentage, total rebounds, total assists, and PER. So you'll notice for field goal percentage, it's a fairly normal distribution. Um, there seems, from the scatter plot, there seems to be a pretty decent correlation between field goal percentage and the total points you scored. Something interesting to note that the points, which are overtime games, tend to group towards the top as overtime goes on, the field goal percentage might not change, but the number of points you're scoring is definitely increasing. So that might skew the data a little bit. So I also graphed one without overtime, and it turns out that the correlation improves to a notable degree from 0.688 to 0.72. And then I pretty much repeated this for assists. Again, normal distribution, a decent correlation, but not as good as field goal percentage, correlation of about 0.57. And I repeated this for player efficiency for the entire team. And unfortunately, the the distribution isn't as good as I thought it would be. Probably because even very good teams with very high PER, like over here on the right, have good games and they have bad games as well. I also did a Shapiro-Wilk normality test because I wasn't sure from visual analysis alone if the PR was normally distributed. But with a p-value of 0.77, it seems to be okay. I also repeated the same thing again for total rebounds, and it seems to be normally distributed, but there doesn't seem to be really any correlation. And this is probably because rebounds is more indicative of the amount of possession you have, but even if you get more rebounds and you have more possession doesn't mean necessarily that you're shooting the ball well. So it's not really telling of how much points you're going to score. So now I repeated that same process again, but with box score differentials and point differentials. So instead of calculating total field goal percentage, I calculated home field goal percentage minus the away team field goal percentage, and then I did home points minus away points for the differential points. So again, I calculate the distribution. They all seem to be normal distributions. And for field goal differential versus point differential, there seems to be a strong correlation between the two. I also calculated that without overtime. Again, this seems to be the highest correlation we have so far, about 0.78, 0.79. I repeated the same thing for differential and rebounds, and not as great a correlation, but definitely better from just the absolute statistic. A correlation of 0.45 roughly. I repeat this for assists again. The final step is to build a predictive model. So the first step I did was to create a function to help calculate the root mean squared error. And then, so I built two models. The first model would predict the points scored at home, and then the second model would predict the point differential for a given game. I split the data into a 70% subset for training and a 30% subset for testing. And I used the variables that seem to have a high correlation, so home field goal percentage and home assists. And I didn't have to eliminate any of the variables because their p-values were under 0.05. And after calculating the root mean squared error, I got a root mean squared error of 8.5 and a multiple r squared of 0.5348. And so I also built another model for predicting point differential. And once again, I did 70-30 split for training and testing. And I did a multiple linear regression model, this time for differential. And all my variables had a p-score below 0.05, so I kept all of them. And I calculated the root mean squared error for 7.35 and a multiple r squared of 0.6845. So slightly better than the linear regression I did for calculating just the total points scored at home. And so using this model, I wanted to predict Michael Jordan's 95-96 Bulls versus the 2016-2017 Warriors super team. The model that I just calculated would predict that the Bulls would lose by about 3 or 4 points.